This is my reassessment video for the modern physics standard. Modern physics refers to advancements in physics from the 1900s to the present. It encompasses a variety of topics. Let's start with wave-particle duality. Photons are particles that exhibit properties of waves in particles. This is why we say light has a dual nature, because it acts like both waves and particles. Evidence that this occurs is the photoelectric effect. According to this theory, when EM radiation strikes a piece of metal, electrons known as photoelectrons are emitted. The only variable that affects this is the frequency of light. The equation for this is the energy of a photon equals hf, which also equals hc over the wavelength. In this, the variable h is Planck's constant. It equals 6.63 times 10 to the negative 34 joules per second. C is the speed of light in a vacuum, which equals 3 times 10 to the 8th meters per second. This is the wavelength, and F is the frequency. Let's try an example. The light has a wavelength of 6.58 times 10 to the negative 7 meters. The energy of this photon is approximately 1. For this, we would use hc all over wavelength. H and c are Planck's constant and the speed of light in a vacuum. We divide that by the wavelength of 6.58 times 10 to the negative 7th meters. After we do this, we get the answer of 3.02 times 10 to the negative 19 joules. Great job! Planck's work extended the theory, stating that photoelectrons would be ejected from the metal only if the photon light was greater than or equal to the minimum threshold frequency. Next, we are going to talk about mass-energy equivalence. This is based on Einstein's work in 1905, which was on the law of conservation of mass and energy, which are concepts that describe the same thing, forming a single law of conservation of mass energy. From these laws, Einstein created his famous equation E equals mc squared, which relates to the amount of energy contained in matter to the mass, speed of light in a vacuum, 3 times 10 to the 8th meters per second squared. Because it is not realistic to convert large quantities of mass to energy, but use nuclear processes to convert small amounts of mass to energy. Mass is so small they are called universal mass units, which equal 1/12 the mass of a single carbon-12 atom. There are two main models in physics. In 1909, Ernest Rutherford conducted an experiment where he bombarded gold foil with alpha particles. As shown in the figure, a source that undergoes alpha decay is placed in a lead box with a small hole. Particles that hit the inside of the box are stopped. Only those that pass the opening follow the line to gold foil and pass through it. Few bounce off the foil. This showed that the atom is 99.99% empty space and the nucleus has a positive charge. The Bohr model describes the electron. Prior to Bohr, it was thought that the electron was like an orbiting planet. Bohr noticed an atom can only absorb certain colors of light and once excited can only release certain energies. This created the energy level diagram shown in our reference tables. Let's try an example of this. What is the energy of the photon emitted when a hydrogen atom drops from the 4th to the 2nd energy level? For this, we would use the equation, the energy of a photon equals the initial energy minus the final energy. Based on a reference table, the second energy level has an energy charge of negative 3.4 electron volts, and the second energy level has negative 0.85 electron volts. After subtracting this, you conclude that the answer is 2.55 electron volts based on information in our reference table. Next, we are going to talk about the Standard Model. In the 30s, it was discovered that protons and neutrons were made of smaller particles. Also, there was antimatter, which is made up of particles with the same mass as regular matter particles, but opposite charges and characteristics. Antiprotons have the same mass as a proton but negative charge. Positrons have the same mass as electrons but positive charge. Antineutrons have the same mass as a neutron but opposite characteristics. There are many forces in the universe. They are consolidated into 4 fundamental forces. In strongest to weakest, they are the strong nuclear force, which holds protons and neutrons together, the electromagnetic force, which holds the magnetic attraction and repulsion, weak force, which is the radioactive beta decay, and the gravitational force, which is the attractive force between objects with mass. In the late 1960s, the Standard Model was created to understand matter and the interaction of strong electromagnetic and weak forces. According to the model, all matter is divided into two categories known as hadrons and smaller leptons. Hadrons are further divided into baryons and mesons. Baryons are composed of three smaller particles called quarks. Mesons are composed of a quark and an antiquark. This is all in the reference table along with particles of the Standard Model. Along with this, there are 6 types of identified quarks. For each, there is a corresponding antiquark with an opposite charge. The name, symbol, and charge are indicated in reference tables. For antiquarks, the symbol is the first letter of the antiquark name with a line over it. Similarly, there are 6 types of leptons also in the reference table shown here. Let's try an example. A neutron is composed of an up and down quark. How many of each is needed to make a neutron? The charge must be 0, and the neutron is a baryon, so it has 3 quarks. Therefore, it is 1 up quark and 2 down quarks, because an up quark has a charge of plus 2/3 electrons, and 2 down quarks are negative 1/3 electrons, which equals 0. Let's try one more example. What is the charge of a down antiquark, which is a D with a line over it? The down quark has a charge of negative 1/3 electrons, so the anti-down quark has a charge of plus 1/3 electrons. All this information is found in our reference table. Thank you for watching, and I hope this was helpful.